All right, let's talk about the bisection method. We're going to break down this super powerful root finding technique, and by the end of this, you'll have everything you need to absolutely crush this on your final exam. So let's dive right in. You've got an equation, maybe from an engineering problem, and you just can't solve it. There's no clean algebraic way to get x by itself. You know there's an answer, but how in the world do you find it?
Here's our game plan. First, we'll cover the basic idea. Then we'll see it work with actual numbers. We'll figure out when to stop, translate it all into code, and then wrap up with the key things you've got to remember.
So first things first, what even is this thing? Well, at its heart, the bisection method is a classic divide and conquer strategy. It's simple, it's reliable, and honestly, it's pretty brilliant.
Think of it like this. You know a root is somewhere in a big field. Instead of searching everywhere, you just draw a line right down the middle, figure out which half the root is in, and completely ignore the other half. Then you do it again, and again, and again.
So here's the magic trick behind the whole thing. If you've got an interval and your function is, say, negative on one side and positive on the other, what does that mean? It means it had to have crossed the x-axis somewhere in between. That crossing point, that's our root. That sign change is the trigger for everything.
Okay, talking about it is one thing, but seeing the numbers actually crunch and the method do its job, that's where it really starts to click. Let's see it in action.
The entire method really just boils down to the simple three-step loop. Step 1, find the middle of your interval. Step 2, check which side the sign change is on now. And Step 3, throw away the half you don't need and make the other half your new, smaller interval. That's it. You just rinse and repeat.
And you can really see what's happening. Those brackets, our lower and upper bounds, they just squeeze in tighter and tighter with every single step. The root is trapped in there, and with each pass, the box it's in gets cut exactly in half. This relentless shrinking is why the method is so reliable.
This table shows you the numbers behind that shrinking box. Look at iteration 1. Our midpoint guess is 125. We run our check and find out the root is actually in the upper half. So, for iteration 2, what do? That 125 becomes our new lower bound. The new midpoint is 162.5. See how the gap between the lower and upper bounds just keeps getting smaller and smaller?
Okay, this leads to a super important question for pretty much any iterative method. How do we know when to stop? I mean, when is our answer actually good enough?
Well, there are two ways to think about error. True error is the dream, right? It's how far your guess is from the real answer. But there's a huge catch. If we already knew the real answer, we wouldn't be doing any of this. So that's not very practical. That's why we use approximate error. It's a clever trick where we just measure how much our answer changes from one guess to the next. When the changes get super tiny, we know we're homing in on the solution.
Now this right here, this is the golden rule for bisection, and you're definitely going to want to remember this for your exam. Your approximate error is basically a worst-case scenario. It's always going to be a little bigger than your true error, and that's fantastic. It's like a built-in safety net. It means that when you stop because your approximate error is small enough, you can walk away feeling confident that your true error is even smaller.
All right, we get the logic, we get the math. Now let's see how this actually looks when we tell a computer to do it. And don't worry, the code follows the exact same simple steps we just talked about. Before the main loop even starts, any good code will run a quick sanity check. It multiplies the function values at the starting points. If that result is positive, it means they're on the same side of the axis, so there's no guaranteed root in between. The program just stops and tells you there's a problem. It's a critical first check.
Okay, this little block of code right here, this is the brains of the whole operation. After you calculate the midpoint, you do that same multiplication test. If the result is negative, it means the root is in the lower half, so you make your midpoint the new upper bound. Otherwise, the root must be in the upper half, so the midpoint becomes the new lower bound. This is literally the divide and conquer step written in code.
And finally, how does the program know when to stop? It's watching for two things. After every guess, it calculates the approximate error, EA. It checks if that error is smaller than some target we set, ES. It also keeps track of how many times it's run. If the error is small enough, or if it's just been running for too long, it breaks the loop and gives you the answer.
So let's boil this all down. You're heading into your exam and you need the key facts. These are the absolute must-know points about the bisection method.
Remember these three things. Number 1, it is convergent. That's a fancy way of saying it's guaranteed to work, as long as you give it a good starting point. Number 2,
Its error is predictable. You always know the interval of uncertainty is being cut in half every single time. And number 3, it's just easy to understand. The logic is simple, which makes it easy to code and easy to trust.
And now for the exam secret weapon. This formula is awesome. It lets you calculate n, the exact number of steps it's going to take to get to a certain level of accuracy before you even start. If you know how big your starting interval is and how precise you need to be, you can predict exactly how many iterations it'll take. That's a uniquely powerful feature of this method.
You know, the bisection method is more than just a tool for one type of problem. It's a perfect showcase of the divide and conquer strategy. This idea of taking a huge problem and just repeatedly breaking it into smaller, manageable pieces is a cornerstone of computer science and engineering. So now that you get it, where else could you use it? That's something to think about.